So what we're going to be doing is I'm going to show you guys how to do a free body diagram. And it's kind of like, in physics we ask you to draw a lot of pictures. Those pictures is really relevant because it kind of helps you visualize what's going on. And that's the thing about physics, it's a very visual science. So I have a question for you, Catherine. What forces are acting? I have a block, or maybe let's make it, I have a side table. You know what a side table is, right? You put it right on the side of your couch.
Yeah.
All right. Let's make it an ottoman. Let's make it an ottoman. This is where you put your feet. It's like a little box that you basically put your feet on.
Okay.
And it's standing on the ground. Here's the ground. Okay? What forces are acting on this ottoman right now? There is a force.
Gravity.
Gravity. I like where you're going with that, but I'm going to burn you, or at least from now on I'm going to burn you with this, is gravity is not a force. Alright? Gravity, when you say gravity, immediately I think 9.81 meters per second squared. It's an acceleration. But if you want to talk about the force that is associated with gravity, we often call that Fg, also known as W, which is mainly known as the weight. So next time I ask you, hey, what force is acting on that? You have to say weight. You can't say gravity because I'm going to turn to you and say, wait, gravity is an acceleration. But weight is totally associated with gravity because that's equal to mass times gravity. Does that make sense?
Yeah.
Because remember, the main equation we're going to use this chapter is F equals ma. And when we talk about a very specific acceleration, the acceleration where a is equal to g, as in a is equal to 9.81 meters per second squared, then we're talking about a very special force that we've given a special name to called weight. All right. Is there any other force that is acting on this ottoman right now?
Ground pushing up on it.
The ground pushing up on it, exactly. And we call that the normal force. Because essentially, is this ottoman accelerating? Is it accelerating up or is it accelerating down? It's not. It's hanging out on the floor. So there needs to be, if there's a force going down, there needs to be an equal and opposite force going up. Does that make sense?
Yeah.
Now, if W got really big, what would happen to N? What is that?
If what?
If W got bigger, what would happen to N?
N would get bigger.
N would have to respond by getting bigger. Now, if W got so big that maybe the ground couldn't hold it, then, W and N will equal each other until maybe W gets so big that, like, you put an elephant on top of the ottoman and it breaks through the ground and then, like, you live on the second floor and then, in that case, W will not equal to N. But for the most part, W will equal to N. Does that make sense?
Yep.
All right. Now, I guess a lot of times people, like, say that we're pushing this ottoman, and say that I'm really short, or maybe this is my little baby who's pushing the ottoman, and he pushes it with a, I don't know, I want to call it FP, as an F push. Now, technically, there is another force that you could write on this thing. There could be the FP. Because if I'm pushing this ottoman with a force this way, the ottoman is actually pushing with a force on me this way, right? Does that make sense?
Yeah.
But in a free body diagram, we want to isolate the object we're talking about. And in this case, I'm isolating the object of the ottoman itself. So I'm only going to include forces that are being acted on the ottoman, not the forces that the ottoman is acting on. What I mean by that is the baby is pushing the ottoman, but I'm not going to include in my diagram the ottoman pushing the baby back. Does that make sense? Alright. One of the things I could do is I could be pushing it at an angle like this. Now let's say an adult starts pushing this thing now. They push down on this ottoman at an angle. What's going to happen to this ottoman? I'm just wondering if you kind of understand this.
What?
What's going to happen to this ottoman as I push down at an angle this way?
It's gonna move forward.
It's gonna slide across the floor like this. And let's assuming that maybe this is an ice skating rink or something like that. So the reason why I would do that is so that we don't include friction. Friction is kind of a different, not a different animal, just an extra complication. But what I would want to do is I would want to make sure to break all my forces up into their components. So if I were to see something like this is my new FP, what I would do is I would probably say, all right, screw that FP, I'm going to break it up into another picture where I have W and I have FPX and FPY. Does that make sense? I basically took this force going down at an angle and broke it up into its two components, FPX and FPY. Now, in order to figure out what FPX is and FPY is, you would go back to that good old SOHCAHTOA, and maybe I can just write it. FPX is equal to FP cosine theta. I don't know. Are you good enough at converting those things that I don't need to step your way through this thing?
Yeah, that's one.
All right. So the FPX and FPY is actually FP cosine theta and sine theta. And that's how you would do it. I have a question. In this case right here, in this case where I have where I'm pushing down at an angle, is N still the same as W? Look at the graph. Look at the picture. Is N still the same as W? Because before you were pushing on it, the normal force was the same as W. But in this case, the normal force is no longer the same as W. I'll prove it to you. If I add the forces in the y direction, is equal to mass times acceleration in the y direction. What is the acceleration of this ottoman in the y direction? It's 0, because it's not going into the ground or coming out of the ground, it's just going across the ground. So, what forces do I see acting on this ottoman? You kind of look at your free body diagram. Name some of the forces that you see in this thing.
What, sorry?
Name some of the forces that you see over here. I want to add up all the forces in the y direction.
I can't really see what you labeled them, but there's the weight pushing down, and then there's the two components of the person pushing on it.
Okay, all right. I like what you're getting at. All right. First of all, let's talk about the weight. Oftentimes, what you want to make sure to include is the weight, and you put a negative in front of that. Why would that be? Well, it's because the weight's pushing down, and I like doing a coordinate system where it's, positive x, positive y. Does that make sense? The second thing is, you said the two components, the FPY and the FPX, and I would disagree with you. I would only include FPY. Also negative, by the way. Why not FPX?
I don't know, I thought we were talking about all of the forces.
Yeah, you're right. But look at what I did. I'm summing the forces in the y direction. FPX is not in the y direction, it's in the x direction. So that's why I didn't include this force, but I did include this one. And then I've got a plus n equals to 0. So if I were to solve that, that would be n is equal to w plus fp sine theta. So your normal force would increase kind of, I mean, if you think about it, if you look at the picture, your normal force needs to balance out these two forces going down, right? This force is pushing down, this force is pushing down. Your normal force has to kind of balance that out. I guess the way I kind of think about it is, if I'm pushing the ottoman down at an angle into the ground, part of my force is going to go into pushing that thing forward. The other part of my force is actually going to be pushing it down. As I'm pushing it down, the normal force is going to have to respond, because not only does it have to counteract my weight, it also has to counteract the amount of force that I'm pushing down at. Does that make sense?
Yeah.
All right. Let's move on to the x direction. That one's pretty straightforward. Sum of the forces in the x direction is equal to mass times acceleration in the x direction. Here's the first question: is the acceleration in the x direction 0? No, because you told me that it's sliding across the floor. It could be accelerating. So I'm not going to just cross that out and equal to 0. If I add the forces in the x direction, I only have FPX. Right? That's the only one I have. And that's equal to mass times the acceleration in the x direction. FPX is FP cosine theta divided by m equals acceleration in the x direction. And all this is saying is that the acceleration that the ottoman will undergo depends on three things. It depends on the mass of the thing. I mean, if this ottoman were super heavy, that acceleration would be really small, right? Because if m got really big in the denominator, your a as a number would actually get really small. It depends on how much you push, but it also depends on the angle. And if you look at this, what if theta were 90 degrees? Let's think about that. If theta were 90 degrees, what's the cosine of 90? Do you know? Do you have a calculator? Are you eating food?
What?
Are you eating?
Yeah.
It's all right. No, don't worry. Keep on eating. It's just I can tell. What is the cosine of 90? Do you know what that is? Off the top of your head?
0.
Cosine of 90 is 0, right? So if theta were 90, then my acceleration would be 0. And I guess if you think about that, that makes perfect sense, because if theta is 90, that means you're not pushing it down and at an angle. You're pushing it straight down. What is your acceleration? Well, you're not going to have an acceleration because it won't be going forward because you're just pushing it straight down. Does that make sense?
Yeah, that makes sense.
All right, cool.